Hello students, welcome back. Today we're going to be continuing with logarithms. Last time we did exponential functions, and now we're going to be studying the logarithms and its properties. So let's go ahead and start with the definition. So for x greater than 0, and a being greater than 0 and a is not equal to 1, we can define the logarithmic function, right, to be this. Y is equal to log base a of x, if and only if x is equal to a to the power of y. Right, so essentially that's what the expression of logarithm means. So essentially, y is equal to log a of x, right, is essentially equivalent of asking, well, what is the x value, right? What essentially a to what power gives us x, right? So a to what power, so essentially a to what power gives us the value. So and it's a to the power of y, right? So a to the power of y will give us the x, right? So they are inverse functions of each other. Okay, so that's essentially the logarithmic function is the inverse of the exponential function. Okay, so what do we want to do? So as an example, right, let's take a look at something. So example 1, we're going to have f of x to be equal to logarithm base 2 of x, and let's say, well, x to be equal to 32. Then my question to you is, logarithm base 2 of 32, what is going to be the value? So what number, to what power 2 has to be in order for us to get a 32? And the answer is 5. Right? Why? Because 2 to the power of 5 will give us 32. Perfect. Now, okay, let's think about the following one. So let's take a look at another example. So let's say we have, again, f of x, we have log based 4 of x, and we say that x is equal to 1. Right, so what are we doing here? We're asking, well, to what power of 4, right, we will get x, so we will get the value. And okay, so that means we're going to have 4 to the power of what? Of 0, right? Because any number to the power of 0 besides 0 is going to be equal to 1, right? So we know, right, for this case, we can make a rule that log base a, to satisfy the definition of the logarithm of 1, will always be equal to 0, right, no matter what base you have. All right, perfect. So now let's go ahead and summarize some of the properties of logarithms. So of course, we already know the inverse property, right, for the exponential, but now let's write them all down. So we have number 1, it's going to be logarithm base a of 1 is 0, because any number, right, positive number to the power of 0 gives us 1. Then logarithm a base a of a, that is the same thing as a to the power of 1, which is equal to a. Then the inverse property, so this one is important. So essentially, right, logarithm of base a of a is just simply x, right? And so for number 3, we can elaborate it a little bit. So logarithm of base a of x. So essentially, right, what we can do, the property of logarithm is as following. We can take x out and multiply it by the logarithm base a of a. So we know by the property number 1, right? So we know that by 1, we have that this is equal to 1, so we have x times 1, which is equal to x. Okay? So that's why we get x here. And then similarly here, we have essentially a to the power of logarithm base a of x, that's just going to be x. Okay, so every time we have something like a to the power of x logarithm, oh wait, no, not like that. So if we have a logarithm of a base a of x, right, so a and a will cancel out, right, and essentially all we're left with is just x, right? So this property is very important. And of course, if logarithm of base a of x is equal to logarithm of base a of y, then x is equal to y. This is a one-to-one property. This is also very important for the function definition. Okay, so why is number 3, the property 3, is important? It's because we can now deal with powers, right? We can deal with powers because sometimes, well, we might not know exactly what number are we going to be dealing with, but because we know those properties, we can simplify. right? So as an example, what would be, so example 3, what would be logarithm base 2 of square root of 2? Right, this is a difficult one, right? In what power, or essentially not as difficult because we know the definition, right? And by definition, so we can have logarithm base 2 of to the power of 1/2, okay? And that is going to be equal to 1/2 times logarithm of base 2 of 2, which is, now it's 1, so 1/2 times 1 is equal to 1/2. Perfect, right? And now we can treat it with any kind of power. It doesn't have to be fractional. It can be a regular power, it can be a negative power. We can do any power of the number, and we can always take it outside. And it doesn't have to be 2, it can be a different number. And logarithm might not always simplify, but we will be able to get rid of unnecessary powers that sometimes can bother us. Okay, now let's take a look at actually a graph, right? We will be talking a lot about logarithm base 2, so let's continue. So let's take a look at the following. Let's take a look at example 4, which would be, so f of x to be equal to 2 to the power of x, right? And then the inverse of it, g of x, is going to be log base 2 of x. Okay, so how would we graph that? Of course, we can do it point by point, but essentially, if we end up doing point by point, which actually, let's go ahead and do it. So we have x, and let's do f of x. The reason why is because logarithm is a little bit difficult to compute, but let's do x and f of x, right? Because sometimes logarithms are not the nicest, but we know in the last lesson we already computed this function once, so you can review the exponential functions in the previous lesson, but let's go ahead and do this one. So we know 2 to the power of -2, that's equal to 1/4. 2 to the power of -1, this is 1/2. 2 to the 0, this is 1. 2 to the 1, this is 2. 2 to the 2, this is 4. 2 to the 3, this is 8. Okay, so we have the values. So now let's take a look at the graph, right? The graph's going to look like this, right? So they are symmetric about the y equal to x, essentially. We have here a mirroring, essentially, of one and the other function. So this is how the logarithm function looks like. And this is our exponential function. Exponential functions are, mostly look like that. So it's just depending on the value and depending on the growth. The bigger the value, the faster we're reaching infinity, right? Because keep in mind that we have a positive infinity here, negative infinity here, and negative infinity here, right? As we approaching. But essentially, that would be the graph. And here, in this case, if we take a closer look, we know that logarithms have an asymptote, right? So logarithm based a of 0, right? So essentially, it's asking us, so a to the power of x is equal to 0. So what power gives us 0? And well, if we take a really close look, it's going to be approaching 0 but never reach 0. So here x is actually approaching negative infinity but never reaches it. So that's why the logarithm doesn't exist. So we do have x equal to 0 to be a vertical asymptote for the logarithm, for any logarithm. For any logarithm that is not shifted, of course. If we shift the logarithm by y amount of units, or any amount of units, right, then the amount of units we shifted it by going to be our new asymptote. Okay, so, and let's summarize in general, right? In general, without any kind of shifting, let's summarize the logarithm based a of x function. So essentially, that's how it's going to look like, right? It will always intersect at x equal to 1, because when x equal to 1, that's going to be 0, right? That's our solution to that equation. The domain is from 0, not included, to positive infinity, range from negative infinity to positive infinity, right? Because it's essentially growing upwards as the x increasing. Then it's increasing on 0 to positive infinity. It's 1 to 1, and therefore, since the function is 1 to 1, it has an inverse, right? That is the condition that has to be satisfied in order for us to have an inverse. And then the y-axis is the vertical asymptote, which is x equal to 0, right? It's continuous, and reflection of graph of y equal to ax and is the line y equal to x. Okay, perfect. And of course, right, let's take a look at some of the shifting, right? We're not going to be graphing, but here we're going to be 2 examples on if we decide on shifting the logarithm, then that's what essentially is going to happen, right? We have, we're shifting it by 1 unit to the right, right? So now our point becomes 2 comma 0, and our function is g of x, that's x minus 1. And here we are going to have 1 comma 0, and we're going to be moving upwards, right? Upwards by 2 units, right? 2 units we're moving upwards, so essentially we're just shifting it 2 units up, all right? So, and now, one of the special kind of logarithms, right? We last time learned about Euler's number. The Euler's number turns out to be an extremely special number because it's also used in natural logarithms. And for the natural logarithms, that's how we call it. It's the logarithms with the base e. And let me go ahead and show it to you. So, the function f of x, logarithm of base e of x is equal to, we have a shortcut for it, which is ln of x. Right, ln of x. So this is very popular. ln of x, where x is greater than 0, and we call it natural logarithmic function. Right, so ln of x means that our base is e. Right, and our inverse, right, if we have y equal to ln of x, so our inverse is going to be, is essentially y equal to e to the x. Right, so that's what we have here, right? E to the x, that was the exponential of Euler, and ln of x, that's also essentially related to the Euler's number. Okay, and some of the properties of the natural logarithms. So let's take a look at that. So some of the properties is as following. So very similar to what we had for the regular logarithms. So it's just a special base, right? A special case. Instead of a, we're going to have just a equal to e. Right, that's essentially what we're doing. We're saying that a is equal to e now, and we're evaluating it at e. Okay, perfect. So now, the way the graph looks like is essentially it's no different than the regular log of a, right? But let's just, for the sake of the looks of it, let's go ahead and graph it. So here it is, right? Here's the exponential to the power of x. Here it is, and it's also symmetric about y equal to x. And here is the logarithmic function. So g of x is equal to inverse of f of negative f x, which is ln of x. And now let's take a look at the shifted graph of ln of x. So similarly, as we had in the regular logarithm, we're going to have this kind of drawings, right? So essentially ln of x shifted by 2 units to the right, and now it becomes f of x, and then g of x is going to be 2 minus x, right? So now it's flipped the direction, and here's an example of h of x is equal to ln of x to the power of 2. So here, it is essential, right? It is essential that h of x equals to ln of x squared is not the same as 2 times ln of x. Right, this is very, very crucial. This is essentially the absolute value here, right? This would be equal to the absolute value of x, right? That's a very important note here for this function. All right, perfect. Now, let's go ahead and actually talk about bases and formulas for exchanging the bases between the logarithms. So now we're going to think about if we have 2 arbitrary bases, a and b, and x to be a positive real number, so similarly as we did in the definition of the logarithm, such that a is not equal to 1 and b is not equal to 1. So we want to convert log based a of x to a different base. Use one of the following formulas below, right? So base b, so essentially the way we can write it out is logarithm of a of x is equal to log base b of x divided by log base b of a, right? And that will lead us to one of the equations. Right, one of the interesting equations that are very, very helpful. Okay, and now we can also have log based 10, right? So this is one of the notations of log base 10. Of course, based on the calculator or based on the app that you're using, sometimes there are different notations. Besides log, there might be lg, there might be just empty, there might be just log with a capital L. So there's depending on the app. How old is the app and how old is the calculator? So, but this is most of the time the general notation of the logarithm base 10, right? This is how they're related. And of course, the logarithm based e, right? We can also always rewrite a logarithm of any base in terms of the natural logarithm. And oftentimes that's what we actually do. So one of the examples we can have as logarithm base 4 of 25, which would be equal to, we can write it as log of 25 over log of 4, right? Or we could do the same thing as an ln. So it's the same thing as an ln of 25 over ln of 4, right? And et cetera, right? Depending on what is more convenient for us for the given problem. So that kind of problems leads us to the intuition of some formulas. So, and those formulas are going to be as following. They are probably the most important formulas for logarithms to learn and remember how to use. So once again, let a be a positive number such that a is not equal to 1, and let n be a real number, and let u and v be positive real numbers. So then the product property of logarithms. So if you have logarithm based a of u and v, then we can have logarithm based a of u plus logarithm based a of v. Same thing for quotient rule, right? Quotient property. So logarithm of a of u over v, that's the same thing as logarithm of u minus logarithm of v. Okay, and same thing for natural logarithm, right? And of course, the power property that we already covered at the beginning, right, with x, but now it's just with real numbers. So logarithm based a of u to the power of n is the same thing as n times logarithm of a of u. Okay, and let's take a look at an example. So an example that we can give here is, let's say we have natural logarithm of 6, right? So then we can rewrite it as logarithm of 2 times 3, which is equal to natural logarithm of 2 plus natural logarithm of 3. So oftentimes it is very convenient because we can cancel things out, right? Subtract or add and simplify. So that is very, very convenient for us. And as an example, if we have natural logarithm of 5 divided by 23, let's say, that's the same thing as natural logarithm of 5 minus natural logarithm of 23. We're subtracting, and essentially the number will end up to be negative. And let's take a look at more sophisticated example. So it's going to be example 7. So let's say we have an f of x. Oh, well, no. Oh, yeah, actually, f of x y is equal to logarithm of 4 of 5x cubed y. Okay, so essentially I'm going to put parentheses, meaning that we're applying the logarithm of base 4 to this expression. So we know by the rules we will have logarithm based 4 of 5 plus logarithm based 4 of x cubed plus logarithm based 4 of y, which would be equal to, right? We can simplify, so log base 4 5 plus 3 log based 4 x plus log based 4 y. Right, so that process back and forth is extremely important for algebraic simplifications, and of course later on that will be very, very useful for calculus applications, because calculus deals a lot with logarithmic properties. And all right, perfect. So this lesson we introduced all of the properties of the logarithms, and we'll review some of the exponentials. Next lesson we will be doing the exponential logarithmic equations and exponential logarithmic models. Stay tuned, and I'll see you guys next time.